and welcome everyone. Let's solve the binary search problem. So we are given an array of norms which is sorted in ascending order. This is important to know that it's a sorted array, and we are given an integer target. Okay, we can just look here, and we want to write a function to search for targets in norms. Basically, we want to look for 9 in this array of integers called norms. If target, this number, exists, then we want to return the index at which 9 exists in these norms. Otherwise, if there is no 9, let's say we're given something like 10, right, we want to return -1 instead. And we must write an algorithm with O of log n runtime complexity. Now, if this problem title was not already a dead giveaway of the algorithm we are asked to use to solve the problem, then the time complexity is definitely a dead giveaway. Basically, you want to use a type of search algorithm called the binary search. Now, if you think about it, there are a number of ways that we can actually search for 9 in these norms. I think the straightforward ways, not the straightforward, one of the ways is we could use includes, right? The array method. We can check if 9 is included, and if it is, then we can traverse the entire array and just write a simple for loop, traverse it, and return the index. Or we can just start with a straight up for loop. We don't even have to check if it's included, and if we get to the end of the array and it's not included, we can return a -1, and if it is, we just return the index at which we find it. But we are traversing the entire array in this instance, and that is going to take an O of n time operation, because basically it's a linear time operation if we are traversing the entire list. But we are asked to write an algorithm with O of log n runtime complexity. This basically means that log n means logarithmic of n, right? If we are to run something linear space, then half of it, which is going to give us log n, like half the time that we would have normally done it. And that is what is called binary search, because we are dividing our given inputs into 2 at every point and only working with half of the inputs given. In computer science, binary search is also called, like I said, logarithmic or half interval, or even binary chop, because this is a type of search algorithm where we are not running a linear operation. Instead, we are running our search operation on only half of the given list, right? And a good example can be like the phone book. Do you remember when we had things called phone books? Or the dictionary, I think everyone remembers the dictionary. If you are looking for an item called queen, you are not going to start flipping the page from A all the way to Q. You just flip to the middle of the dictionary and flip again till you get to Q. You don't have to start opening every single page of the dictionary. And basically, that's what a binary search is. Our input array is already sorted, right? The target is 9. So if we split this into half, I don't want to cancel out that number. So if we split this into half and we look for our middle number here is 3, right? And we check, is 3 greater than 9? No, it's not. So we just know that, okay, this particular side, right, of this particular half of this array is not going to give us what we want. So we can just focus our search on this side of the array. That's the point. We don't have to, once we get the middle of the array, the middle of the inputs given, we don't have to traverse the entire list. We don't have to traverse the entire list to search for this target. We can just search for the middle number, which in this case is 3, and we can just, okay, this first middle, the highest number here is 3, and you know that this right half is definitely where our target is going to be, right? And if it's that is not there, at least we've narrowed the search. For instance, if we have something like 10, then we don't even have to waste our time on this part at all. We can just spend our time here till we find 10. And even for this part, where it's more likely that even for this part where it's more likely that our answer would still split it into two, right? Just to narrow it down till we find the last input given. Let's assume the input given here is 10, because we want to be sure, right? We don't want to waste our time traversing this entire thing. If we find the middle of this second half and the middle is 9, then we don't need this half again. We don't need 5 anymore, because we have 9 and we know that, okay, 10 is greater than 9 and 10 will only be after 10. And this can only work because the array is already sorted. So to run a binary search, our given input, which the data structure is always going to be an array, really, you can only run, well, so far I've only tried to run a binary search on an array. I've not tried to run it on any data structure. I think array is the default that you can run a binary search on, but the array must be sorted input. So that's dead giveaway where you want to determine what kind of search algorithm you should run when you're told the exact logarithmic runtime complexity. Only binary search really does things in splits in half the time given. I mean, that's the best time complexity. The worst time complexity, CO of log n, half the given input, and the array also has to be sorted. I feel like we've already gone through the walkthrough without even giving ourselves extra room, but just to be sure, we're just going to go through it. So let's say we are given the following numbers. We're given 1, we're given 0, we're given 3, we're given 5, 9 and 12, and we want to find if 9 is in this given input, right? So what are we going to do? Use a binary search. Binary search method means that the algorithm means that we have to find the middle value, right? And we can find the middle value by taking the index. Let me just write the index above them. So the index of the first value and the last value, this is 5 plus 0. And if we should floor this is 5 plus 0, which is 5, divided by 2, right? The half is going to be 2, actually 2.5, but if we floor it is exactly 2. So we know that this is our middle number. So we want to check our target. Is our target greater than our middle number? If yes, then we want to discard this entire side of the operation. We don't need it anymore. We want to discard it. Then what do we do after discarding the entire operation? Then we want to move our, remember that we got this middle by adding the highest given index plus the lowest index, which was 0. But now we want to move this lower index. It's no longer going to be 0. It is going to be our middle index, which we don't need anymore. We've agreed that it's too low for our scope. We're not going to find our targets there. So we want to increment our middle index plus 1. So our middle index is going to be 2 plus 1. No, we previously had 2 as our middle index. Plus 1 is going to give us 3, right? Our upper index, basically the scope of how we find the middle, stays the same. So now if we try to find the middle again, we're doing 5 plus 3 is the index. Don't forget, we are summing up the index, not the actual numbers. 5 plus 3 is going to be 8, and if we floor it, we are going to be given 4. So our new middle index is 4, which is this, right? Our middle index is 4. This is our middle index now. So we check, is our middle index, the value at our middle index, the middle index is 4, is the value at this index, which is 9, is it equal to our given target? And yes, it is. And so we just return 9. In the instance that our middle index is let's say 10, right? If our middle index is 10 and we floor this value and we have 4, so we check this 4 and it's for our given index. No, 4 is not our given index. So we check that is the value at 4, rather, not 4 itself. Is the value at 4 our given index? No, it is not. We are checking the indexes. Then we are, when we want to get the middle pointer, right, or the middle value, we are using the indexes, or the indices rather, to get them 5 plus 0, 5 plus 3. But we have to now check the number at that index, because it's the number we really need, not the index themselves. So we now check, right? Fine, we've gotten that, okay, 8 divided by 2 is 4, is the number. Now, don't forget, we're working the assumption that 10 is our middle index. So we're saying, okay, is 10 is the number at 4 the middle index? 1, it's not the middle index. Then we check, okay, is it lower than the middle index? Yes, it is. 9 is lower than 10. So that means from here on, we do not need all this anymore, because it is lower than 10. Now we update our pointer to this place, whereby our lower, since we know that, okay, our answer is not going to be here, right? 10 is greater than all of the values here, so we don't need all of those numbers. So we move our pointer. Our upper pointer is going to be here, our lower pointer is going to be here. 5 plus 5 is going to be 10. 10 divided by 2 is 5. So this is going to be our only value left, and we can just see that, okay, it is not equal to 10, it is not less than 10, it's not greater than 10. Basically 10 is not in this operation, so we can just safely return a -1. Now I'm just going to go over this again before we run quickly to the code walkthrough. Now we are given our target is 9, right? And we want to check if 9 is in this operation. So what do? We find the middle of the number, because binary search means that we are running our operation on only half of the number. We are running our operation on only the part where it is more likely that the target would be. Since this array is already sorted, we don't need to run through the entire thing and make this a linear time operation. So we would only run this operation on where it is more likely that we'll find 9. That's the basic thing about binary search. So we want to find the middle, and we find the middle by getting our first operation is getting the first index and getting the last index, like basically the length of the last item, and then we are summing it of 5 plus 0 and flooring it by 2, basically getting the half. Like if you want to get the middle number of an array, this is how you do it, and this is going to result to a value of 2, and the element at pointer 2 is 3. We are going to check if that value is equal to the target. No, it's not. Is it greater than the target? No, it's not. If it was greater than the target, then we know that we don't need this part, right? We just need to focus on this part. But in this case, it is not greater than the target. So we're basically just going to, you know what, we don't need you then, since this is less than the target. Definitely there is nothing in this place that is going to give us what we need. So we don't need this, and we need to update our lower pointer, right? We want to update our lower pointer to the current middle plus 1, which is going to be this. Then we can continue our operation from here. But if we were looking for a number, such as if our target was, let's say, 2, right? If our target was 2 and our middle number here is 2, then we can see that 2 is definitely less than the value at index 2, because the value at index 2 is 3 and our target value is 2, right? So that tells us straight up that don't waste your time checking this right hand side. You really don't need it. Focus on this side. What do we do in this case? Recall that when we are trying to look for if our value was larger, we updated our lower pointer, but in this case we're going to update our upper bound. You recall that our upper bound was 5, but now we're going to move our upper bound to the middle, and the lower bound will remain 1. So we'll only be working with these confines. We'll bring down our upper bound to the middle, because we don't need this place. It is simply too large. The code is going to make it clearer if you don't already get it. So let's jump right into the code. Alright, at this point I'm going to ask that if you are not yet subscribed, please consider subscribing, and if you also like this video, please consider giving it a thumbs up, as it definitely helps the channel. So let's jump right into the code. First, we are going to define our lower and upper bound, and initially our lower bound is going to be the first element in the array, or the first index, which is 0, up onto the last index in the array, like basically the length of the array minus 1, right? And while lower is less or equal to upper, we want to find the middle, right? The middle is just going to be what we showed in the code walkthrough: upper plus lower. This is the floor division in Python, where we are going to be giving the rounded down figure, right? So if the if the target is if the target, I can't spell this morning, if the target is equal to the middle number, then we've gotten it and we can just return the middle number because we are returning the index, not the actual number, right? But if the target is greater than the middle number, if the target is greater, then we know that we are shooting the right bound is too far, and we want to, if the target is greater than the middle number rather, then just like we showed in the code walkthrough, we want to increase our lower bound so that we are not far off and the left side is basically not needed for us. Else we just want to, else that means that the target is lesser than the middle number, and in this case we want to increase our the point at which our middle number is reading from. If after all of this iteration we still don't have our answer, then we want to return -1. That means that your number does not exist in this operation. So I'm just going to run this code first and then submit it. So I also want to try something new by solving this problem in JavaScript. I don't know, I want to test it out, see if it helps more people. Yeah, so let's just try this out. So first we are going to define, just like we did with the Python code, we are going to define our lower bound as 0 and our upper bound as that is going to be norms.length -1, and while lower is less than or equal to upper, we want to find the middle, which is going to be math.floor upper plus lower divided by 2. And I think that I just want to put this in extra brackets. So just like what we did, we just want to find the target. If target is equal to the middle value, we know that we have found what we want and we just want to return that iteration. If that's not the case and target is greater, I keep forgetting the braces, and target is greater than the norms, then we want to update our middle pointer. Else we are going to update the upper pointer, which means that the right bound is too far off. And if after all of this operation we still haven't found our number, then we can just return a -1. All right, let's run this code and let's try to submit it. Okay, and this works. Like we discussed, the time complexity is what they've already given us. We have to solve this in log n time, and we didn't use any extra space. So this is also 0 of 1 space complexity. That is our complexity analysis. Thank you so much for watching. I'll see you in the next video. Bye.